Today we're going to be discussing changes of state. Now, first off, let's get one thing clear. A system of particles is always moving, it's always vibrating. Now, if that system has a higher energy level, the vibrations are going to be stronger. It's going to move more. The particles in the system will have more freedom to move about. And if the system has a lower energy level, the vibrations will be weaker. The system's particles will only vibrate in smaller movements. Just keep this in mind throughout this entire chapter because it's going to help you understand these processes in a much easier manner. Now, since you know the three states, that's solids, liquids, and gases, you can know that they are interchangeable. There are processes which take you from one state to the other, independent of the other one. First off, we have melting. Now, if you see here, this is a solid. It's got a regular patterned placement of particles. This is called a lattice. That's Lattice. A lattice is a structure in which the particles exist in a regular and equidistant form. The particles themselves have a very lower energy level. They only vibrate in small movements. Now, if you give this lattice, this solid piece over here, if you give it energy in the form of, say, heat or light, it's going to convert into energy for the particles. Now, those particles are going to start vibrating harder and harder in proportionate to the energy that it's receiving. So you see how here in this intermediate phase, you see how these particles are getting more and more energy. And slowly, all the particles are going to get as much energy and they're going to change into the liquid form, which means that now these particles are not so closely bonded together. The intermolecular forces are not so high, and they can hence now slide over each other and exist in the liquid form. That's melting for you. Next, we've got boiling, which is the change from liquid to a gas. Now, much like melting, this process involves applying heat energy or light energy or any form of energy, to be fair, to a certain amount of liquid, like you see here, and giving the particles energy. And once these particles, they reach it one by one, as these particles reach the energy that is corresponding to their boiling point, they receive enough energy to break free from the level of the liquid, and they escape into the atmosphere as gases, as you can see here. And this happens over time, as in a liquid or in any state of matter actually, the particles exist at different energy levels. The ones with an already high energy level will be able to achieve the energy level required to break free from the liquid level at an earlier time. And over time, all the particles will receive the energy required to break free, and hence all these molecules that are liquid over here will turn into gases, into gas molecules rather. Next, we've got evaporation. Now, evaporation you might think is similar to boiling because it is technically the same state change. It's liquid to gas, but the process is a little different. Now, as I mentioned, particles in liquids or any state of matter are at different energy levels. Now, in this liquid, some of the particles which have a higher energy level, like these ones over here with the blue vibrations coming off them, indicating they've got high energy levels, might just collide with other particles and exchange momentum and exchange energies and get even higher. And sometimes what happens is these particles get enough energy to break free from the surface and escape as gas molecules. An example of this you can see is after the rain, you'll see a puddle dries up over time, even though you know for sure that the temperature outside in the atmosphere is definitely not near its boiling point. So there's no way that rainwater could have reached the energy level required to be converted to liquid. So what's happened there is that all the molecules in that puddle have been converted to gas molecules by the process of evaporation. Next up, we've got freezing. Freezing is essentially the opposite of melting. They technically occur at the same point. So what that means is the freezing point and melting point of a substance is going to be the same, except that the process that is occurring will happen in the direction of which the energy is flowing. So say supposing you're giving a substance energy at the freezing / melting point, then what's going to happen is it's going to melt. Whereas if you take away energy towards the freezing point or melting point, what's going to happen is that substance will end up freezing. It's going to lose energy. Now the process of freezing is pretty self-explanatory. What happens is, if you've got a liquid here, as you can see, and you're taking away energy from it, you're extracting energy from it, you're cooling it down maybe, or you're taking out all the light or something like that, which will reduce the energy in the particles. Now these particles will slow down, they're gonna start forming into a pattern like structure, they're gonna get equidistant, and soon suddenly all the particles will not have enough energy to be free-flowing liquid molecules anymore. They're going to turn into this lattice structure, and as we all know, solids exist in the lattice structure, and hence you have now received a solid. Next up, we've got condensation. Now condensation is the process in which gas molecules are converted to liquid. It is very similar to freezing, as it occurs when gas molecules lose out on energy and they start losing the distances between them, and they start getting more and more attracted to each other. The intermolecular forces start getting stronger, and what happens is they lose out on energy and they come together and they form a liquid, like so. Like over here you can see all these molecules, they're very free flowing. You can see that these can move in any direction, they've got a lot of energy. But as you're taking out energy from this area, you're taking out energy from these molecules, you see that they can start moving in lesser directions. They start coming together, and soon in the end you've got this liquid where all the molecules have lost out on enough energy to convert all of them to liquid. Sublimation is a special kind of process because it occurs when a solid is given enough energy at a high enough rate to directly convert it from a solid straight to a gas. Next we move on to a phenomena as such called Brownian motion. Now I'm going to explain this to you in a simple manner. If you see this molecule here, it's numbered 1. Okay, and you consider that the start point, and you see this one over here, number 14, and you consider that the end point, and I tell you how would this particle travel from this position to that one. You would say it probably goes in a straight line. It goes from this point to the other point. As you know, the shortest distance between 2 points is a straight line. But the thing is, between this point and this point, there are a million, a trillion, a bunch of other molecules that stand in the way, that offer resistance to its motion, to its path. So what happens is, this molecule with the energy that it has is going to collide. It's going to collide with this particle here, to this one, to this one, to this one. It's going to bounce back and forth and left and right and round and round. And then it's going to find itself through random motion, through random collisions between particles at the point where it says 14 here. So it's a random uncontrolled movement of a particle because of colliding with other particles that change the direction of the aforementioned particle indefinitely and constantly. An example of Brownian motion is diffusion, which I have depicted here in the form of this tanker, which contains, say, two liquids, and one of them is blue in color, these molecules over here. And at one end, I drop in these four molecules of the red liquid from here. Now, diffusion would mean that the randomized movements and collisions between these particles is going to cause these four molecules to spread out evenly over time via colliding between each other and the other blue molecules, the blue liquid molecules in this tanker. And over time, it'll reach a point where they're all spread out evenly, as you can see at this right hand side diagram over here. This is an example of Brownian motion. Now we move on to the last topic of this chapter, gas pressure and temperature. Okay, so imagine this tanker, this enclosed space in which I have trapped 1, 2, 3, 4, 5, 6 gas molecules. And I have tracked the paths of 3 of them. And as you can see, these gas molecules are constantly hitting the sides and each other and exchanging energies and momentums, right? And when that happens, there is a change in the momentum of these particles. Now, this change causes or creates rather a pressure on the inside walls of the container by the gas when they hit it. Therefore, what happens is these gas molecules exert a pressure. A live example of this could be when you take an empty bottle and if you put it in your mouth, the open end of it, and if you suck in, what you're doing essentially is taking out all the gas molecules, the atmosphere, the gas particles of the atmosphere which were in it. You're pulling it out with your sucking action, and what that does is as you'll know, it's going to crush the bottle. It's going to, and basically what that is that the inside pressure that was being maintained by the atmospherical gas molecules that you have currently taken out are no longer putting that pressure that's keeping the inside of the bottle up against the outside pressure from the atmosphere that's pushing on it, and hence it's been crushed. Two relationships that you must remember is that the faster the particles of gas are moving, the greater will be the pressure exerted if you're keeping the volume same. As you can see here in this container, the volume is completely the same throughout. And this is because the particles will collide with the walls more often, and hence they will do it with a larger force. Now, gas temperature is the measure of the average kinetic speed of the particles. Now, the faster the particles are moving, the higher the gas temperature would be. Once again, if you keep the volume the same, as the average kinetic speed of the particles will increase. That's it for this chapter.